Very good afternoon to you all. So today in today's class and the previous two classes, we have seen the calculation of the reactance, and we have got reactance of a transformer windings. So in this particular class, we'll be considering how to design the tank and cooling tubes for the transformer. So this class will govern how to design tank with cooling tubes for transformer. So prior to the design of the tube and this thing, uh, why the cooling tubes are provided? Definitely in a transformer, especially the three-phase transformer, the cooling tubes are provided for two purposes. One purpose is for cooling, obviously insulation and cooling, because high voltage transformers, the temperatures go beyond certain point. It contains some oil and some amount of air in the radiators. So we are supposed to design a tube and cooling arrangement for a transformer. In case of transformer, the tank and cooling tube are provided for basically for cooling purpose. So the tank contains air and oil. So the tank contains air and oil. So number one point is the tank contains air and oil, whereas in the tubes, in case of tube contains only oil as a medium. Tube contains only oil as a medium. It contains only oil as a medium. This oil is provided to absorb the heat energy dissipated. So we have to limit the heat energy dissipated, and this oil should have high viscosity. So whenever I'm writing an up arrow, this would mean high. So this is high. So it should have an high viscosity and high, it should have density. It should have high density and it should have high dielectric strength. Whereas it should have, now I'm writing like this, it should have obviously low cost, and what else, and it should be low in impurity. It should be pure. So impurity. So how do we go about the design of the tank and tube? That is our main goal in this particular lecture. So how we go about this is, what we do is we make an elementary design diagram. So how the arrangement looks like. So the arrangement of tube and coil, the primarily arrangement looks somewhat like this. We have an arrangement like this. Where this is the length of the tube and this is the width and this is the height of the tube. So herein we can write down WT as, let WT you can see WT. What is this? This is the width of the tank. And dimension would be in meter because it's a length. Similarly, your height of tank and length of tank. HT is your height of tank. HT is your height of tank. Height of tank. Again, this would be in meter. And your LT is your length of length of tank, length of tank. Now what we are interested in, so we are interested in the dissipating area, the S, the total dissipating area, which looks like a cuboid, so it would be 2 LTST plus 2 STW2. If you are going for the calculation purpose, so it would be STLT plus STLT plus STWT plus STWT. See here, it would be twice STLT plus twice STWT. So this is the surface area. So this is your surface area, that is the dissipating surface. We have not considered the bottom portion, we have just considered the top portion. So this is the surface area of dissipating surface area, and this would be in meter square. We can write S is dissipating surface area, and it would be in meter square. Now what we are interested in, we are also interested in to understand, let us suppose, in this particular arrangement, let's consider X to be as specific heat dissipation. Now because of the tubes and because of the transformer arrangement, we have some amount of heat transfer. Now the heat transfer process is by three processes, that is, one is direct conduction. If we touch one surface with another, that is one process. Another process is by convection, that is when two bodies are meeting, and then a hot and a cold body is meeting, and then that absorbs and you get an equilibrium temperature, a different temperature. For example, you are mixing two liquids, one is at 50 degrees, another is at 20 degrees, so you after some time arrive at an average temperature. That is called the process of convection. And then you have the process of radiation, like for example, your earth heats up, and then in the afternoon usually you find more heat compared to the noon time, because your earth's surface is also radiating some heat, on top of that sun is giving some heat. So there is process of radiation, convection and conduction. So here in this particular arrangement, what we are having is, we have the heat is transferred from one place to another by three different ways. One way is conduction, convection or radiation. In case of tank, now we are considered, we have two things, tank and tube. So in case of tank we have both radiation and convection, whereas in case of tube only convection occurs, as the tube carries only oil. So we can write an important point here. I hope you have noted down this thing. So this is design of tank with cooling for transfer. Okay, so in case of tank, what happens? Radiation and convection. And in case of tube, only we are having convection because it carries oil. So here we are interested to calculate. Calculate. So let theta be the temperature in degrees Celsius, and let W into T be the heat dissipated by each tube, and let N be the number of cooling tubes. Here we are interested to calculate what we are interested, that we know that the dissipating surface area is given by 2 WTST plus 2 LTST, but what we are most interested here is to find out what amount of specific heat dissipation is observed due to convection and radiation. If for example, let's suppose X be specific heat dissipation due to radiation, and it's a standard. Due to radiation, the specific heat dissipation is 6 watts per meter square per degree Celsius, whereas specific heat dissipation due to convection, earlier case was radiation, and the second case, let's suppose it's Y, specific heat dissipation due to convection is 6.5 watts per meter square per degree Celsius. So we can write down like this. Let X is equal to specific heat dissipation due to radiation. Similarly, let Y be the same thing. We note this is specific heat dissipation due to convection. So how we will arrive at these two particular points? So the two particular points we can write down. So we know our surface area is given by S. So this surface total specific heat dissipation by tank due to radiation and convection, we can write down like this. Now total like heat dissipated by tank due to radiation and convection can be written as how? We know the total surface area of the tank is given by S. So heat due to convection, total surface area is S. So heat due to convection would be S times that is your X times S theta. Similarly, heat due to radiation would be X times S theta. Similarly, heat due to convection is Y times S theta. So this is a standard is 6 watts per 6 watts. The heat due to convection is given by 6 watts per meter square because the surface area per degree Celsius. Similarly, this is 6.5 and the unit is same, that is watts meter square per degree Celsius. So we can write down this as 6 times S theta plus 6.5 times S theta. So total how much we are getting? 12.5 S, 12.5, this is 5 S theta, and the unit would be total heat dissipation. The unit of heat is given by in watts. Now this was about the tank, but we have to also consider the surface area of tube. So the tube would be inserted inside the tank. The surface area of the tube would depend upon the dimension, that is the diameter of the tube. So and it would depend upon the height of each tube. So if we give the diameter of each tube as D and height of each tube as H, so the surface area due to the tube would be, if D is diameter of tube and small h is height of tube, so the surface area due to each tube would be given by surface area, in this case would be pi d h. It is basic your mensuration 10th class, meter square. Now the position of the cooling tube is such that the heat dissipated by each tube would be normally 1.35, 35 to 40% more compared to the tank. So what we write that heat dissipated by each tube, if that is given by Wt, is around, we will consider like 35%. In this case 1.35 times the heat dissipated, because heat dissipated by the tube is due to only convection, so we will only consider this 6.5, and this is 6.5 times 6.5 times the normal rate. So this would be heat dissipated by the each tube would be 6.5 times into your 1.35, and now the surface area of the tube would be not exactly the of tank, it would be a fraction of the tank, that is your x times st. So the heat dissipated by the tube can be given by 8.8 x st. So this is somewhat we are arriving at. Now let's go from the very beginning. This was the some prerequisites which were required for understanding. Now let's go from the very beginning and let's start the derivation and how we will go about it. Let the dissipation surface of the tank be st. Okay, let's suppose the dissipation surface of the tank be st. So dissipation surface surface of tank is how much, is equal to st. Okay, now the dissipating surface of the tube is, it will not be exactly st, it would be x times st. Dissipation surface of tubes would be x times, let this be equation 1, equation 2. Now the loss dissipated by surface of the tank by radiation and convection, that is loss dissipated by tank surface due to radiation and convection. Already we have derived this. Due to radiation we have 6 watt per meter square per degree Celsius, and due to convection we have 6.5 watt per degree per meter square per degree Celsius. So this would be total would be 12.5 times st. So let this be equation 3. Now we have the loss dissipated by tubes. Now the loss dissipated by tubes is only by convection, so the loss dissipated by tubes would be given as, and already we have calculated that, that is your 6.5 into 1.35 into x times st, that is your 8.8 x times st. This is your equation 4. Now the total loss dissipated by walls and tubes. So the total loss dissipated by walls and tubes would be your equation 3 plus equation 4. So this total loss would be equation 3 plus equation 4. So the total loss, how you are going to calculate? You are going to add these equations. So I'm rubbing this surface. Let's calculate the total loss. Total loss would be how much? Total loss would be your 12.5 st plus, this is your st, plus 8.8 x times st. So what you can do, you can take st common, so your total loss would be 12.5 plus 8.8x. let this be your equation 5. Now actual area of tank walls and tubes. So actual area of tank walls and tubes, area of the tank was st and area of the tube is x times st. So the actual area of tank walls and tubes would be your st plus x times st. So actual area of tank walls and tubes would be st plus plus x st. So this total area would be, you can keep st common, 1 plus x. So this you got as equation 6. Now you have to calculate the loss dissipated per meter square dissipating surface. So loss dissipated per, so total loss you know is this and total area is this. So loss dissipated per meter square, loss dissipated per meter square would be, per meter square dissipating surface would be what? It is simple, it would be this total loss, that is your 12.25. This you can st, that common you have taken, 12.5 plus 8.8x, that is your equation 5 divided by your equation 6. So your equation 6 is this, st 1 plus x. So here you can see your st, here you can see st and st cancelled, here you can see st and st cancelled. So st and st cancelled, so you arrive with 12.5 times this st and st cancelled, so you arrive at 12.5, 8 plus 8.8x, 1 plus x. Now temperature rise in transformer with cooling tubes. This is your equation 7. So now you will go for the temperature rise, because we have to calculate how much temperature rise would be there. So the temperature rise would be given by your theta. Theta is your temperature rise, and your theta would be temperature rise in transformer. Temperature rise in transformer with cooling tubes. So temperature rise theta depends upon the total loss. So the total loss depends upon your iron and your loss in your core. That is, your total loss would depend upon your P iron loss and your P copper loss. That is your Pi plus P copper divided by your loss dissipated. This means your total loss divided by your loss dissipated per surface area. So this you can see total loss is P iron plus P copper, and this you can write the equation 7 which we had calculated, and we calculated equation 7 as the loss dissipated, that is the total loss dissipated by the walls and tubes. That is not equation 7 but the earlier equation, that is your I think equation 4 or 5. You can see that loss dissipated, and this equation would be 12.5 plus 8.8x times st. So from here you can calculate the value of x. You can calculate the value of x by combination. See here you can आराम से calculate the value of x. This is Pi plus P copper, 12.5 plus 8.8x st. So finally you will get x as 1 by, even if you want I can do it for you. This is your Pi plus Pc, and this is here theta times st. What I have done is nothing. I have taken this Pi plus Pc and theta I have brought down. Here I have brought down and I am taking this here 12.5 plus 8.8x. Now you need to calculate the value of x. If you keep here, see here, so you can get x is equal to 1 divided by 8.8 Pi plus Pc theta times st minus 12.5. Let this be your equation 9. This is the equation for x. So now you know that you have calculated the value of x and you have total area of cooling tubes given as x times st. So total area of cooling tubes you can calculate by this particular equation by multiplying this equation by st. So equation 9, if you multiply by st, you will get total area of cooling tubes. So total area of, this is equation 9. So total area of cooling tubes, if you multiply equation 9 with st, you will get total area of cooling tubes. So total area of cooling tubes is nothing but as st multiplied by equation 9. So st, so total area of cooling tubes, total area of cooling tubes would be x into st. X you have calculated, that was your in the previous you have calculated, that is 1 divided by 8.8 pi plus pc theta st minus 12.5 into st. If you do so, here this cancels, this goes, so here you can cancel this with this and you will have a value of 8.8. 8.1 divided by 8.8, so this would be 1 divided by 8.8, here pi plus pc theta minus 12.5 st. This is the area, total area of the cooling tubes. Now one important thing is that you have to calculate total number of tubes. If you want, you need the total area of tubes which you have calculated and area of each tube. So area of each tube also we have calculated. Area of each tube would depend upon what? It would depend upon the length of the cooling tube and the diameter of the cooling tube. So area of the each tube, if you see, would be how much? It would be equal to, area of each tube would be equal to pi times diameter of the each tube and length of the each tube. So area of each tube, you can see, this is, if you can consider, this is your equation 11. Area of each tube would be, pi dt lt. That is your length of the cooling tube and diameter of the cooling tube. Now if you want how many number of tubes you require, number of tubes, that would be x times st, that is x times st divided by pi dt lt. So if you solve this equation x times st, so you have to substitute this value 1, and for here you have to substitute this value. Finally you get the expression. That expression I'm going to write it down here, and that expression would be, final expression, that expression would be, n would be equal to, your nt would be equal to 1 by 8.8 pi dt lt pi plus pc theta minus 12.5 st. So here are some, this is the design of the cooling tubes, how we arrive at the number of tubes which we will require for the equation, and there are some clearance associated with it, so certain theoretical points which we'll be discussing in the next class, and we'll be solving one important numerical associated with it which has come in video examinations, and I hope you will grasp the concept, and stay safe, stay at home. This is Corona time and we will defeat it together. Thank you very much for your patience and kind cooperation.